Okay, so today we're going to do MO practice. So it's just basically drawing two MO diagrams. We're going to do chlorine and we're going to do ammonia. So we'll look at a polyatomic and walk you through this. This is something we've seen in parts. We've seen the chlorine one. We saw fluorine completely. And come all the way as far to the front as possible. Those that just came in. But because we have time to go through this in detail, please ask questions. Don't worry about being on your voice being on the video or anything. It's not a big deal. You really can't hear your question too much on the video, so it's not like anybody can identify you. Okay, I won't call out your name. Okay, so let's go ahead and dive in. I'm going to run this on the full screen. So we'll do this. That way you can see what I'm doing on the board. And I'll try to be as detailed as possible. But if you can't see anything, I can erase and come on as close to the front as possible. I know you cannot see this from back there, so. All right. So let's see. The first one, let's draw the MO diagram of chlorine. You okay? Yeah, it's okay. I think we're okay still. Yeah. Now, one thing that we'd like to know in terms of the diatomics that we were talking about in class, and that is one, does it contain that SP mixing that kind of mixes up the levels? And there's only a few diatomics that applies to, and essentially it's everything from nitrogen to the left. Okay, and so from oxygen on, which includes chlorine, we don't have SP mixing, and so we're going to have the two p orbitals, or the pi bonds in the middle, and then the sigma bonds on top and below the pi bonding region. Yes?
Does the SP mixing work for like phosphorus?
No, it's just those tiniest little atoms on the second row. Yeah, so that's the only time we have to worry about it. Yeah, so the way we do an MO diagram, give ourselves some space. So as far over on the left of your paper as you can, draw one chlorine atom. And then over here as far right as possible, draw the other. And so these two atoms, this is meant to spatially show these two atoms far apart are just atoms. But as they come together, they form the chlorine molecule. So in the middle, strange, we have the chlorine diatomic. And the z-axis is the axis of the molecule. We can draw our little coordinate system. So we've got the z-axis defined, so counterclockwise is the right-hand rule. And so we have x up here and y coming out at us. So that will define the px, the py, and the pz orbitals. And it will tell us if the pi bonds are in the x or y direction as well. And it'll tell us which, on the antibonding, which one's xz and which one's yz. So let's draw the atomic orbitals. So we have, this much space. So right about here, make a third of the way up, draw your three p orbitals. And then about a third from the bottom, draw the s orbital, and we'll label those in a second. It's a homonuclear diatomic, so these are going to have the same energy. So straight across from those p orbitals, draw three more in the s orbital. So if this was a heteronuclear diatomic, let's say we were doing like chlorine oxide, ClO, which side would be lower? The chlorine, oxygen, well, they have kind of the same electronegativity. I was going to say use the electronegativity as your guide. Let's go with the halogen being a little bit lower, has more protons. So we would draw, again, if I had to guess, I'd say the chlorine orbitals were a little bit lower than the oxygen ones. Okay. But this is a homonuclear diatomic, so they're going to be straight across from each other. All right, let's go ahead and fill out the electrons in these. What are the valence electrons for chlorine? Oh, let's label them, actually. So this is an s and some p orbitals. Which s and which p's are they? Yeah, so chlorine, we come right across and we see it's in period 3. So it's going to be the 3s and the 3 p's. And let's go ahead and label these x, y, and z. I was just being picky and put ZYX on this side so the Z's are close to each other. They're kind of from the middle out, they're the same. Okay. Any questions so far? Let's put our electrons in. Okay. So 1, 2, 3, 4, 5, 6, 7. You see how I did that? I put them on all unpaired and then I started pairing them up. So 1, 2 in the bottom, 3, 4, 5, 6, 7. So let's do the same over here. 1, 2, 3, 4, 5, 6, 7. So those are my atoms. They're coming together. They're going to start interacting. The 2 P's, 2 s orbitals, and then the 1 s orbital are down here in the core, and they don't interact with bonding. So we don't even show them in our MO diagram because we're showing the bonding arrangement, the molecular orbitals that are formed by the valence electrons coming together. Anybody need any clarification? Yes?
Shouldn't your x and y's be the same? Because on the left-hand side, you got one electron z.
Yeah. So that's a good point. Let me go ahead and make this one the unpaired. I don't know that it matters, but we'll be consistent. How's that? Okay? Great. And so let's now bring them together. We have 2 s orbitals coming together to interact. They can be in phase or out of phase, meaning they could be the same color, expanding together, or one expanding while the other's contracting. And so we'll draw those, one in a bonding arrangement, one in an anti-bonding arrangement. I don't want to go up too high because I'm going to get too crowded up here. So I'm just drawing them down here. I'm going to draw the dashed lines just to show where those orbitals came from. And I'm going to go ahead and draw the pictures of these. You may want to bring to the exam, some colored pens. It'll make it easier. So those are, I'm just really drawing the spheres for the orbitals. So these are both the same color. If it helps maybe for the screen to shade them in. And these up here are a different color, just to indicate that this top one is expanding and contracting out of phase with each other. Okay. Any questions on mixing the S's? No nodes down here, one node right there, increasing energy. So now let's bring the Pz orbitals together, end on. And so I've got some nice little atoms here. So these Pz orbitals are going to be coming together. Let me zoom in here on the picture. And they're going to be end on like that. Or maybe this way. You can see how they come together. All right. So they're able to overlap favorably. And so that's where the electron density is going to be, where they're overlapping. And that means it's going to be stabilizing these two nuclei, who without the electrons would repel each other. So the only thing holding these positive nuclei together is the electron density between them. Okay. So the Pz's are going to come together in phase and out of phase. And here we can see two nodes. We see a node here, here, and now we have three nodes up here. So even though we have an expanded box, we've got high curvature, so that increases the energy of the wave function. And here we have even more energy, more curvature to the wave function. Again, curvature is related to the number of nodes. If it's curving a lot, it's got to go through 0. And that's what we're showing with the different colors. All right. And now let's bring in the pi interaction. So let's label these sigma and sigma star. This one's sigma, sigma star. Now let's do the px orbitals. I'm going to draw it over here. And so as those come together side by side, if the green sides are on the top and the red sides are on the bottom, that's a favorable interaction. If they're opposite, then it's not. My little pictures here are just so if they're the same color like this, that's the bonding interaction. So those two p orbitals can interact side by side. But if they happen to be out of phase, they'll come along and there's a node in the middle. And so if there's that node in the middle, that's the antibonding. So this would be a pi bond, side-on interaction, and this would be the pi star. So the antibonding interaction. So that's what we're trying to draw on the board in 2 dimensions. The figures in the notes have these drawn as a double line. I like to set them side by side. So that's the bonding interaction. And then we'll draw the antibonding. I miss that tray every time. Because I'm trying to hurry. Okay, so there we have it. So this is pi, and this is pi star. Don't mess this up. Sometimes I ask how many nodes a molecular orbital has, and they see this one. The students see this one, and they say it has 0 nodes. But there is a node in the plane of the bond. So there's a node here that you shouldn't forget. So there's one node there, and there's one here, and then one here in their plane. So there's a nodal plane here that contains the bond, and there's a nodal here that breaks the bond. Nodal plane there. One question I have, if you were to be given these pictures, can you see that all of the sigma interactions have what I call rotational symmetry? If I spin that orbital around the bond, it just doesn't change at all. But if I spin this pi bond around the bond, the top becomes the bottom and the bottom becomes the top. So it does not have rotational symmetry. I mean, it doesn't have a +1 on rotation. These have a +1 on rotation. This would have a -1 on rotation. If I rotated this to C2, then it would change color, and I would call it a -1 on rotation. So pi interactions do not have that +1 on rotational symmetry that the sigmas do. So that's one way to tell if it's a sigma interaction or a pi interaction. The other way to tell is where the electron density is. So if we were to square the wave function, that's the probability density, right? And so essentially all the colors go away because you're squaring everything. All the minuses and positives become the same color. And so where are the electrons in a sigma bond? They're along the axis of the bond. Where are the pi bonds, if you squared them? They're above and below the bond. either star or pi star. They're above and below the bond. There's no electron density on the bond. Okay, so that's another way to tell if it's a sigma or a pi interaction. All right. Now let's put our electrons in. We came in with 7 electrons on either side, so we have 14 to distribute. Okay, so we start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8. Look what I did there. Unpaired first. Okay, 7, 8, 9, 10, 11, 12. See that? Okay, unpaired first. 12, 13, 14. So we have all of our electrons in there that both atoms brought in. Not all of them are bonding. We have some antibonding electrons here and some antibonding electrons there. And so we could add up those bonding electrons and subtract the antibonding electrons. And since it takes 2 electrons per bond, we could divide by 2 and figure out how many bonds we have. So let's count those up. I have 2 down here, 4, 6, 8. So 8 bonding electrons. And then I have 2 in the antibonding here, 4, 6, 6 antibonding electrons divided by 2. Okay. A minus 6 is 2 divided by 2, so I have a single bond. And that should match what we see in chlorine as a single bond. It matches the force constant, it matches the bond length, it matches the vibrational frequency, all of those different things that you would expect from a single bond. And it all fit on the screen. Okay. So you can watch this over and over again if there's any kind of questions you have about that. But now's the time to ask for clarity. This is all the pictures. These are all of the one thing that's not on here is the symmetries. Okay, so let's look at the symmetries. We have this D infinity H character table. Okay, it's in the previous set of notes if you need to look that up. So let's get our symmetries for the different orbitals. What was the 3s orbital? Well, because this is D infinity H. That's the point group. Okay, so we go find that character table. It has G's and U's because it's got an inversion center, and so the top row, spherical things are going to be in the top row. So s-orbitals are at the top row. That's going to be A1 for top row, and it's G's and U's, so it's going to be a G. So A1G for the 3s. And those are going to mix together. And so they're going to mix together here. They're going to produce A1G here. This one, though, is going to be the z-axis. And so we look in the character table, and we see that it's also A1G. That Z is up on the top row of the character table. It can't be G, though, because it's going to be inversion. So A1U. Yeah, A1U. And then our Z's, PZ's, we find that's going to be A1U. Is that correct? Okay, see that in the character table, the PZ here, A1U. This one, this sigma bond, if you look at that, that's going to be an A1G orbital, okay, because it looks like Z squared. If I stand on the center of that molecule and look left and right, the colors look the same. Okay, so that would be Z squared. You find Z squared in that character table. It's going to be A1G. Up here, this one is going to be, if I look right, I see green close to me and red far away. If I look left, I see red close to me and green far away. So that's going to be the opposite sign of looking right. Just like the Z-axis. If I look on the Z-axis and I look to the left, I see positive numbers, increasing Z. If I look to the right, let's see, yeah, my right, I see decreasing values. So all the same numbers, but the sign has changed. And so if the sign changes looking left to right, standing on the center of the molecule, then it has the symmetry of that axis. So if I'm looking this way, I'm looking positive in Z. I have numbers going on to infinity. They have positive signs in front of them. I look this way, I see exactly the same numbers, but now negative signs in front of them. If I look at this orbital, I'm standing in the middle of that molecule, and I look right, I see a certain positive-negative pattern. I look left, I see the same numbers, but different signs on every one of them. And so that's just like the z-axis. Same numbers, different signs. So this would be the symmetry of Z, which we look up, and that's A1U. And then the Px and Py, we just have the Px's shown here mixed together. The Py's would be the same pictures, but rotated 90 degrees. They're a little more difficult to draw. The X symmetry and Y symmetry, if you look those up in the character table, what do we have? E1U, okay. E1U. And so then this one is going to have the same symmetry as the x-axis. If I stand on that molecule and I look up, I see numbers with a certain sign indicated by the color green. And if I look down, I see the same numbers but with the opposite sign indicated by the color red. Okay, so up is the same numbers, opposite sign as looking down. So that's the same as the x-axis. If I look up on the x-axis, I see positive numbers. If I look down, I see the same numbers but with the opposite sign. And so this is going to have X symmetry, which is E1U. But look at this one. This is one of the ones that I wanted you to recognize by pattern. And so let's just call the green positive. So I'm going to say positive, negative, around the origin of the molecule. So when you see that positive, negative pattern, you know two axes are being multiplied by each other. You just need to figure out which axes are being multiplied by each other. So what is the plane of the board here? Z and X. You see Z and X are in the plane. Y comes out of the plane. Okay. And so if I take the positive X values and multiply by the positive Z values, I get a positive region of numbers. And if I take positive X times negative Z, I get a negative region. And so we get that same pattern of X times Z. So this is XZ symmetry. And we look that up on the character table, and what do we see? E1G. E1G. So this is E1G. So now that I have the symmetries, I could do selection rules. And so if I ask you what's the HOMO and LUMO transition, what is the symmetry setup for the HOMO and LUMO transition? We can identify the highest occupied molecular orbital. These in here are all our molecular orbitals. So these are the MOs. We just need to find the highest occupied MO. It's not that one, it's this one. This is as high as my electrons go. So this is the highest occupied molecular orbital. Really both of those, it's a degenerate set of orbitals. And then of my unoccupied orbitals, that's the only one I have, but it's the lowest energy. If I had multiple ones, it would still just pick the lowest. And so this is the LUMO, the lowest unoccupied molecular orbital. And so many times, the visible light, if you're going to have a molecule that's colored, it's most often the closest two orbitals, and the closest two orbitals that are the HOMO-LUMO gap. Those, if I were to excite this to some other orbital, it'd be a longer arrow, which means a shorter wavelength. It'd be in the UV. So the longest wavelength absorption is going to be the energy levels that are closest together. It's going to be the shortest arrow in any of these diagrams. And that's going to be the HOMO to LUMO transition. So our strongly colored, dyes and pigments and so on, they have a HOMO-LUMO gap that's in the visible region. And so we could draw this arrow and say, what is the symmetry selection rule for this transition? So it'd be the pi star to sigma star transition. It'd be the HOMO to LUMO transition, same thing. And we have the E1G to A1U. And we had to figure out what can cause that transition.
One more time, what is that transition called?
the HOMO to LUMO transition. That's one way to say it. The pi star to sigma star. So you just look to see what kinds of orbitals are being joined. A lot of times we'll label those as well. We'll say this is a pi to pi star transition, or in this case it's a pi star to sigma star transition. For water and ammonia, you have non-bonding electrons, and so you might have N to pi star or N to sigma star transitions. So you can have non-bonding electrons, sigma bonding electrons, pi bonding electrons, sigma antibonding, and pi antibonding. And that's pretty much it. There's really 5 possibilities: non-bonding, and then the bonding and antibonding, sigma and pi. Okay. So how would we set this up? Well, we would do the transition dipole moment. Where we have A1U and E1G. And light would go in the middle. So we try to figure out what possible type of light can cause a transition from an E1G to an A1U. And so what are our choices for light? Well, light can be X, Y, or Z, and we have those things on here. We have an A1U for Z, and we have an E1U for X and Y. Okay. So let's try the X and Y, because I've got E1 and I've got an E1 here, and I know that E1s and E1s times each other will give us top row. So let's do E1, E1U. And so you would want to go to the direct product table to find the multiplications, but I've done this a lot, so I think I have this memorized, where I've got, well, I know I have G and U memorized. So what is U times G? U, very good. So we have a U here. We know our results are going to be U. But I've got an E times an E, so that's going to be 3 things. It's going to be an A1, an A2, and an E. Okay? And so excuse me for covering it up. So the E1 times E1 gives us these 3 pieces, A1, A2, and E1. And you'd have to check my work because I'm going off of memory here, but just check those A1, A2, and E. But I do know that it does give an A1 because anything times itself will give an A1. Okay. And then these 3 are used because of the GU transition, or GU rules. Now I take this A1U for the sigma star state and multiply by all 3 of these terms. A1 times anything gives that thing back. Okay, so this is going to give an A1, an A2, and an E1. So I multiply by all of these, and I get this set inside my integral of A1 plus A2 plus E1. And so what GU symmetry do I have? I have U's times U's. These are all G's. So what do I mean by these plus signs? Well, these are various functions that are added to each other, and we're integrating the whole thing. So it's really 3 different integrals. And if that integral is of a function that's not the top row, it's going to be 0. But here's one that is top row. So because we have this right here, this A1G, this integral, which is indicated by the Dirac notation, this integral has a term that's non-zero. So this transition will be allowed. So the HOMO to LUMO transition in chlorine is an allowed transition for direct absorption of light. And if it's an excited chlorine molecule, it could emit light directly. So an electron could drop down and emit light. Okay. So that's pretty much everything I could ask you about this molecule. Yes?
When we're doing it on the test, so we tested X and Y, do we have to test Z also?
Yeah, it would be a good idea to test Z, so we'd bring A1U in here.
Okay.
And so it'd be A1 times E1, which would bring E1 over. And it would be U times G, so it'd be U. So we'd have an E1U here. And then it would be E1 times A1, which is going to be E1 again. And it would be E1G. So we could look at that. I mean, we could do it again, but it would be E1 would come, let's see, yeah, E1 would come down and it would come down again. And so in the end, we would have E1G as our result. Yes, it's G, but E1's not top row, so it would not be allowed for Z polarized light. So what do I have to do? And it does kind of make sense. If I've got an orbital that's got X character, and I want to put it in an orbital that has Z character, I've got to do something with that X character. So light has to come in with some X motion to sort of cancel that motion out and get the motion back on the Z axis, which is compatible with the upper orbital. So even visually, you can see if I've got motion in the electron cloud like this, light has to come in and hit that cloud to get it to go in the Z direction. And then that electron can hop up into that Z direction orbital from an X or Y direction orbital, because light has come in and sort of knocked that out of the X plane and into the Z axis. So this is one of the things that is conserved from classical physics into the quantum realm, as they say, is the conservation of momentum. And light comes in with momentum, and it uses that momentum to cause these transitions. And what we're trying to see is, does the momentum work out with symmetry? Very difficult math buried under these integrals, but we can look at the symmetry and understand when certain transitions are allowed and when certain transitions are not. So Z-polarized light could come in, and it really wouldn't interact with this orbital. Okay, so it could not cause that transition. But X or Y polarized light could come in and cancel the X or Y nature of this and cause the transition. Okay. So let's look at some of the more complicated ones since we're about halfway through. Last chance for questions on Cl2. Okay.
Okay, so you said that we only do the XZ. Do you want us to draw the XY or the YZ on the exam for the 3P?
Oh yeah. So it's getting so busy, but yeah, if you would, do your best. Okay, so what is our best? Let's draw that one real quick. I'll try to cram it in here underneath. So here we have this one, and how do I know where to draw these little things? Where's the red? This is it. Look up here at this y-axis. Look at the angle of that y-axis. It's like 45 degrees down. Okay, so that's going to be the angle of my p-orbitals. So I'm going to draw, let's see, this one here. Going back. So when I draw them at that angle, I'm trying to make them the same angle as the y-axis, so that when you see that angle in these pictures, you recognize, oh, that's the y-axis angle. So therefore, these are coming in and out of the board. You see that? It's really attention to detail. That's why I said this is not just chemistry, it's art. And the better you are at sort of drawing molecules and representing them, the better you are at making arguments using those pictures. And most of the time, we do science at the whiteboard before we ever get to the PowerPoint, before we ever get to the paper. And so being able to draw is a really useful skill. I remember my inorganic professor could draw cubic structures and I could see them in 3D. I mean, it was amazing. I was like, I want to be able to draw like that. And I couldn't. Guess what? Practice. Okay? The more you do it, the better you get. Yes?
So for all the d-infinity H molecules, is the setup going to be the same like all the
Yeah. This is, once you learn it for like a diatomic, a homonuclear diatomic, this is it. The only difference you get with a heteronuclear diatomic is that atomic orbitals shift a little bit, and that's it. So you just have some sort of, the lines are not symmetric on the outsides, but the middle looks the same. Yeah. And so really the SP mixing is just kind of a weird thing for those small, second row diatomics. And so if you just know this pattern here, then that's good for almost all of them. And if you were to draw this for something like carbon or whatever, technically you'd be wrong, but 90% of it would be right. Yeah. Maybe 95%. Yes.
In your PowerPoints previously, you numbered the sigma star.
Oh, yeah.
Star. Do you want us to unnumber them?
Yeah. Those numbers there's no agreed upon way, so that's why you see I didn't put any numbers on these at all. Yeah. If you were to force me, I would just number them from lowest to highest, and I would call this one 1 and 2 and 3 and 4. I guess 4, 5, 6, 7, 8. I would just number them in order, so I could talk to you about orbital number 2 or orbital number 8. Yeah.
So if we don't number them on the test, it's okay?
Yeah, it's
or-
okay. It's totally okay. Yeah. If you were to if this was what you did on the test, that would be beautiful. 100%. Yeah. Yes.
So for heteronuclear molecules like carbon monoxide,
Yes.
for the XP mixing, would that be present or negative?
I don't know, and so that's the thing. So if you just draw it like this, you're good. Yeah. So I really want you to just learn this. That's the bottom line. The SP mixing, we just wanted to show the book had the finer details with that. But if you were to just learn this would be great enough. Yeah, I'd be happy with that. I'm really happy if you can do this. A lot of folks just really, don't quite get there as much as I try. But if you could repeat this, then you're doing well. Or if you get one of these and you can answer questions about it, it takes kind of a while. It took us 30 minutes. Now I was talking during the whole time. But if you were given one of these, could you answer questions about it? That's another thing too. Yes.
If you're doing a HOMO-LUMO transition, but you define a diradical, how would you want that explained? Or you don't need to worry about that?
Like in oxygen, where you just had, it'd be the same. Yeah. So you're just taking one of these electrons from the HOMO to the LUMO, and so it's yeah. The only thing the diradical does is it might change the exact energetic position of these orbitals a little bit. So it would move the wavelength, but you would still have distinct HOMO and LUMO. And it wouldn't know. Actually, I wouldn't be able to tell you if it came from that one or that one, because they both started from the same energy, and I can't really get into the molecule and see, which orbital did it come from? Yeah, so there would be no way for me to know that experimentally. Yes?
So is it kind of like a rule of thumb that when you multiply E and E, it's going to be A1, A2, and E?
Yeah, prove it to yourself by looking at the direct product table, and you'll see in every situation. Do you have it with you?
Yes.
Okay, let's look at that.
I guess just for on the E2, is that different? Is it
Oh, yeah, so E2, yeah, let's see, A1. Yeah, so it looks like when they're multiplied by themselves, you get the E2. So I'm looking at, see if I can get this on here. If you're looking closely here, I'm wrong on the E1. So these should be 2s right here. Yeah. So I'm going to correct this. Like I said, I'm kind of going by memory. And so this is a 2 and a 2. Okay, it doesn't change our result, but it's nice to be correct. So thank you so much. Now this was using the direct product table for C6V, D6, and D6H. The D infinity H will be similar in terms of the E and multiplication rules. But if you'll notice on C3V, let's see. Yeah, up here, C3V. In C3V, you don't have E1 or E2, so you just have E. So here's the C3V one right here, and it's just A1, A2, and E. Okay, and so anytime you have that, now think about it, you've got a two-dimensional thing, an E times a two-dimensional thing, so you ought to have 4 things in the end in terms of their dimensions. And you have an A, which is a single, another A, which is a single, and an E, which is a double. And so, again, you bring in a thing that has 2 dimensions each, you multiply them, you ought to get 4 dimensions, and you do. When I mean dimensions, I think of just the symmetries, different wave functions. And so they have different properties, and so we could call those independent dimensions. We're not talking about like different dimensions in space, but we're saying, different character, something that has, but those Millikan notations, the E rows, they have a dimension of 2. There's X and Y, or XZ and YZ. Yeah. So, thank you, that's good. Now, again, there's not a lot in the book about this because this is adding in that Cotton and Wilkinson book material, the symmetry selection rules. But if we don't do the symmetry selection rules, then why do we even have symmetry in a course? And otherwise, it's just trivia. This molecule is D infinity H. Yes?
So for the homework, I think we're practicing the MO diagrams.
Yes.
Also ask about multiplicity. What
Oh, yeah,
spin
multiplicity.
down would we use?
Sorry?
What spin up, spin Like which one would be?
Yeah, so we're looking at this, we have all spin paired electrons. And so there's no net spin. If we had a spin plus 1/2, we have a spin minus 1/2. And so all the spins have canceled on this one. So the net spin is 0. So, let's use orange for that. So, I'll just sort of point at this net spin equals 0. Okay, and so that's, I would say S net spin is 0. So 2S plus 1 is equal to 1. Right. So the multiplicity 2 times S plus 1 is 1. So it's a singlet. It's a singlet. Yeah. And even after absorption, so that electron hops up here to the LUMO, the allowed transitions, you can't flip a spin and absorb. And so it just still stays a singlet. So even when the electrons are in different orbitals, you still add up all the spins. So we might have, an electron here like that and another one up there that's spin down. So we have a plus 1/2 here and a minus 1/2 there. The net spin is still 0. So this is still a singlet. Even though it's an excited singlet, it's still a singlet. And that would be a singlet to singlet transition. So this is a whole atom now with the orange. That's a whole excited chlorine molecule. It's still a singlet though. And then when that electron was down here with the black electrons, the whole molecule is the ground state chlorine molecule, and it's a singlet. And so the absorption is from a singlet molecule in the ground state to a singlet molecule in the excited state. Now, if that electron unpairs through, which one is it? Intersystem crossing or internal conversion? Intersystem crossing, because you have a change in multiplicity. So if that electron flips, then you have an excited triplet state for the chlorine molecule. And then it can't easily radiatively de-excite. It can't easily spit out a photon. If it does, that's phosphorescence. If this just drops back down, that's fluorescence. If it flips and gets kind of stuck in the triplet state and then flips and emits, then that's phosphorescence. These are great questions because they tie in the other material from the electronic spectroscopy. Yes?
This is diamagnetic, right?
Yes, the way, in both situations, if the electrons are spin paired and has a net spin of 0, it's diamagnetic. Yeah. What if I hit this electron with enough energy to emit it from the molecule? And so then we have Cl2 plus, just a single plus. So we've ionized it. What's the net spin? I just have one unpaired electron. We just always assume it's plus. It doesn't matter. So plus 1/2 is the net spin. If I've ionized it, I've pulled one electron off. I have Cl2 minus plus 1. So it's plus 1/2 is our net spin. And the multiplicity is 2 times 1/2 plus 1. So that gives me a doublet. Yeah. Okay. Another faster way to do that, I have one unpaired electron, plus 1 is a doublet. Okay. 0 unpaired electrons, plus 1 is a singlet. 2 unpaired electrons, plus 1 is a triplet. And they can get more complex. You could have 4 unpaired electrons, plus 1 is a quintet. Okay. Just like in the symphony. We have beat this one pretty hard. Let's see. Okay, if I take out 2 electrons, it's isoelectronic with which diatomic? So look at the periodic table. I got Cl2, and I take away 2 electrons. It moves left. Yeah, O2. Is that right? No, S2, sorry. Wrong row. Okay. Yeah. So I take Cl2 neutral, and I ionize it. I knock out 2 electrons. And now I have, taken 2 electrons out, and it has 2 unpaired electrons. It's a diradical. It's Cl2. It's isoelectronic with Cl2. The reason we have to remove 2 electrons to go left one space is because it's a diatomic. Okay. If I move just one electron, it's not isoelectronic with any neutral diatomic. So just think about the electrons and the molecules. I mean, you can make cations, anions, and neutrals. And if you want to talk about isoelectronic, you're not worried about the nuclei. You're worried about the electrons. You know, so you're just looking at, is the electron cloud like this diatomic or that diatomic? Yes, Patricia.
So the other day we looked at chlorine as hydrogen.
Mhm.
Could you explain again why there was such a big difference in the two one, the s-orbitals?
So if this was like HCl?
Yeah.
Yeah, okay, so the hydrogen here, we would just put the 1s orbital pretty high because it doesn't have a lot of protons. And so the 1s orbital would be up here and the chlorine atom orbitals would be here. And the only thing that could really interact with it would be the Z coming right at that s orbital. And so for this one, I would have just a ball on this end, a green ball, and then up here I'd have a red ball. And so the Pz orbital would be, this green would be pointing at a red 1s orbital on hydrogen, and so it wouldn't overlap and that'd be antibonding. But down here, the green would go over the whole hydrogen if I had a green 1s orbital here. So that's all you would have, is just mixing with that 1s orbital on hydrogen. And it'd probably be too far away from these, from the 3s to interact. Yeah. Does that help?
So
Okay.
would it be similar if you say you had sodium and bromide?
Yeah, I think so, because you just had that 1s occupied orbital. You might have, yeah, I would probably do that because, again, that sodium has just got that, in that case, a 3s orbital, and that's where the valence electron is, and so it's going to be pretty high. It's going to be that frontier orbital. Yeah, so that'd be great. Wow, we pushed it all the way to the end. One more question, 1 minute. That one that's been burning in your imagination. Okay. All right. Have a good day.